Hello students, and welcome back to another lovely day of chemistry. In today's lesson we're going to start talking about limiting and excess reactants. Realistically, you already know what this is in real life, but sometimes it maybe doesn't make sense in chemistry terms. So a limiting reactant, remember reactants being the things that are, if you picture a reaction, reactants being the things on the left side of the arrow, and then you have your products on the right side of the arrow. So when we're doing chemical reactions, we typically need to look at, is there a reactant that's holding us back? Is there a reactant that's not allowing us to make more of our product? An excess reactant is a reactant that we would have extra of. And I'll get more into this as we look at the next slides. So here's a familiar example to help explain what this limited and excess reactant means. And again, I'm going to try and just write this out as a chemistry problem to kind of show what I mean. So here, if we have a chemistry problem, we could say 2 tires plus 1 frame is equal to 1 bike. We'd have our reactants over on this side, and then we would have our product on the other side. So here's this question. If I had 12 tires and I have 50 frames, how many bikes can I make? Well, for the most part, you can probably reason this. All right, I have 12 tires. For every bike that I want to build, I need 2 tires is equal to 1 bike. Tires are going to cancel out, and hey, look at that. We'd be able to produce 6 bikes. If we did this the other way, though, and I wanted to take a look at frames, well, if I have 50 frames, and I converted that into bikes, well, for every 1 frame I can make 1 bike. Well, according to my frames, I should be able to make 50 bikes. So in this case, our limiting reactant, that is the thing that's limiting us from making more product, or really just what's holding us back, is going to be our number of tires. We just don't have enough tires to build all the bikes that we would want. And why? Because the tires run out first. And that makes frames then are our excess reactant. Why? Well, we have extras. This exact same thing applies to chemistry. Sometimes when you do a reaction, you're probably going to have more of one reactant than you would of the other. Or, just to give you one more example for the activity that you'll be doing in class, is let's think of this in terms of s'mores. So when you make s'mores, you need 2 halves of a graham cracker, you're going to need 3 pieces of chocolate, you're going to need 1 marshmallow. And what that's going to allow you to do is to make one of this entire thing that we call s'mores, also known as G2C3M. So 2 graham crackers bonded to 3 pieces of chocolate bonded to 1 marshmallow. Well, let's pretend for a second that you're going to make s'mores, you're out camping, and you have 8 pieces of graham cracker, 15 pieces of chocolate, and 5 marshmallows. Well, one of these is going to hold you back. One of them is going to stop you from making more. So in this case, if you have 8 pieces of graham cracker, what we can do is we can convert that into s'mores, because for every 2 pieces of graham cracker, I can produce 1 s'more. So therefore, 8 graham crackers, and we're going to bring our 2 graham crackers per 1 s'more, so this is just our conversion. This is the exact same thing when you look at that sheet of paper. This is the same as going from moles of A and converting to moles of B. It's the exact same step. So we're just going to convert from graham crackers to s'mores, and we see, all right, I'd be able to make 4 s'mores. With our 15 pieces of chocolate, well, for every 1 s'more I produce, I need 3 pieces of chocolate, so I could produce 5 s'mores. If I have 5 marshmallows, well, guess what? I need 1 marshmallow per 1 s'more. I could produce 5 s'mores. So in this case, our graham cracker pieces are limiting because we're going to run out of them. Our chocolate pieces and marshmallow are in excess because we would end up with extra left over. And let's try this with a more complicated example, and I'm actually going to teach you the way that I have students solve for limiting reactants. there's a lot of different ways to do it. You could solve for how much product can you make, but another way to do it that a lot of times is easier is you can actually just take one of your reactants and solve for the other, and that tells you how much you would need. So let's see this in action. If I have 45 graham crackers and 72 pieces of chocolate, which is my limiting reactant? Well, all right, this one's a little bit harder to just reason. So the easiest method, and that's why I have a star on here, the easiest method is to start with one reactant, such as we'll just start with pieces of graham cracker, and solve for the other. So if I take my 45 graham crackers and solve for C, what that answer is going to tell me is that in order to use all of my 45 pieces of graham cracker, I'm going to be solving for how many pieces of chocolate would I need. So let's go through and solve for this and see what it looks like. So we're going to start with our 45 graham crackers. I'm going to need 2 graham crackers for every 3 pieces of chocolate. So 2 graham crackers for every 3 pieces of chocolate. That way I can have my graham crackers cancel out. And if we plug this into a calculator, we get an answer of 67.5. But because I know we all love sig figs, I'll make sure to round here. Realistically, since these are exact conversions, that 2 to 3, we ignore those sig figs. So we're going to round this. We would need 68 pieces of chocolate. So again, what that number tells me, what that 68 means, is that in order to use up every single one of my pieces of graham cracker, I would need exactly 68 pieces of chocolate. Well, guess what? Earlier in the problem, we said we have 72 pieces of chocolate. We only need 68. So what that tells us is that graham cracker, this would let me ever write, graham cracker is what's holding us back. Graham crackers are limiting, and that we're actually going to have chocolate is excess. Because in order to use up all of my graham cracker, I only needed 68 pieces of chocolate, but I have 72. Or we could have done this the other way, and we can use this as a way to double check our work. Instead, I could say I have 72 pieces of chocolate, and we're going to see, well, if I wanted to use up every piece of chocolate that I have, let's just convert to graham crackers. So again, I need 3 pieces of chocolate for every 2 graham crackers. Chocolate's going to cancel, and in this case, you're going to get an answer of 48 graham crackers. So again, what this number tells us is that in order to use up all 72 pieces of chocolate, we would need 48 graham crackers. Well, we only have 45. So again, this helps us confirm that our graham crackers are limiting and our chocolate pieces are in excess. That is, we have extra of them. This slide is really just kind of explaining what a mole is again. Please remember that a mole is 6.022 times 10 to the 23rd of something. So when we keep using this word mole over and over throughout these problems, it's, again, that's talking about quadrillions upon quadrillions upon quadrillions of atoms or molecules. And the reason that we need to know that is, you know, if we picture like a lithium atom bonding to something huge like an iodine atom, which has tons of energy levels, right? Atoms don't care about the physical size. So ultimately, when we are doing these reactions, we need to compare numbers of moles, not grams. And the reason for that is while the mass of something is important, ultimately atoms are going to base on an amount. They're going to bond based off the number of atoms, not on the actual mass of the atoms. So mass is great because it's a way for us as humans to measure it, but realistically, atoms don't bond based on mass, they bond based off of how many there are. And that's important to keep in mind as we go through this, just like with s'mores. I didn't care about the mass of the graham crackers or the mass of marshmallows or mass of chocolate. I just knew I needed 1 marshmallow to 2 graham crackers to 3 pieces of chocolate. All right, and in this slide, we're going to talk about this more in terms of a actual chemistry scenario. So let's say we had this reaction where we have 3 sodiums reacting with aluminum chloride to produce sodium chloride and aluminum. Let's say real world, we just have 12 moles of sodium and 1 mole of aluminum chloride. And again, this is just a ratio saying that for every 3 sodium, you need an aluminum chloride. Up here, it's saying we have 2 moles of sodium and 1 mole of aluminum chloride. So to convert this, again, we're just going to do that moles of A to moles of B. And so if I look at this, I have 3 moles of sodium, or I need 3 moles of sodium for every 1 mole of aluminum chloride. And so following my sig figs, this will give an answer of 0.66 repeated. With sig figs, that means that we have we need 0.7 moles of AlCl3. Well, again, we have 1 mole of AlCl3, and we only need 0.7 moles in order to use up all of our sodium. So what that tells us, our aluminum chloride is in excess, our sodium is going to be our limiting. And we can answer that down here as well. We need 0.7 moles of aluminum chloride, and that means that Na is our limiter. It's going to run out first. And just because I know y'all would be mad if I didn't do this, I have to throw in some mole jokes for you. What did Avogadro say when you mixed ice cream, chocolate syrup, and milk together? I'm trying to remember some of these. I want to say that this is going to, of course, be a chocolate mold. I mean, obviously. Was a mole's favorite soda? Alright, I think he has 2 of them, because I honestly don't remember. It's either Coca-Cola, but I think it's actually, I'm pretty sure I remember, it's actually Molten Dew. Pretty sure it's Molten Dew, because it's definitely better than Coca-Cola. What's Avogadro's second favorite hairstyle? Oh, I know his second one. I don't want to give away his first one. It is obviously the Mohawk. And what did Austin Powers say when he met Avogadro? Oh, I need to show you a video. I'll show it to you the next time we're in class together.